Yeah, that's what I wanted to do. Oh, yeah.
All right, let's go ahead and get started. I'm going to hand it off to Julie to introduce the special guest.
Okay, well, I'm not going to do very much introduction either. Sean from headquarters is here, and he is the head of astrophysics. And he is going to say a few words of, well, welcome is a little bit odd because we're in the middle of the meeting, but a few words of greeting.
Yeah, so for context, I was hoping to be here on Monday to give a few words of welcome. I couldn't do that because I was in Alabama visiting our teammates down at Marshall Space Flight Center, checking out their X-ray optics and seeing some other cool stuff. So I'm Sean Donegal-Goldman. I'm the acting astrophysics division director at NASA headquarters. I just wanted to share with you all, not just, I mean, people come in and they do the welcome spiel and they say like how much they love Roman, how excited they are for the work that you're doing. I'm the Astrophysics Division Director. Clearly that's true. I love what y'all are doing. I love the Nancy Grace Roman Space Telescope. I think the other thing that's really exciting to share is not just that me with my biases as in that role, that I'm not the only one that's excited about it, right? That the Nancy Grace Roman Space Telescope was the top recommendation of the Decadal Survey, and now it's barreling towards the launch pad successfully with congressional support, with support in the president's budget request, which means that we have a high degree of confidence that we're going to get to that launch pad. I'm feeling really good about it, and I'm feeling even better about what Roman will do to change our view of the very fabric of the cosmos that we're speaking to each other in about a year. I know there's questions about the budget for the rest of astrophysics. I'll just say continue to watch the appropriations process and see how that plays out, and continue to watch the agency and see how it responds to that. I can't say much. In fact, I'm not even supposed to be doing these public spiels. I did it because we ran into each other over coffee, and I wanted to share not just how excited I am, but how excited everyone is for Roman. So like, this sounds like a cliche, but like keep your heads down, keep doing fun, awesome stuff, and then see how the process plays out. And we'll see you at the launch pad. All right? All right. Thanks, everybody.
Take care.
I wish I could stay, because this is more fun than anything I do in my daytime.
Me too.
All right, so with that, we're going to kick off our last session of the day. And we're going to start with Michelle Namaka, who's going to tell us about machine learning.
All right, thanks very much. Can everybody in the back hear me all right? All right, excellent. My name is Michelle Namaka. Today I want to talk to you about trustworthy machine learning for astrophysical discovery. We are a little more than halfway through this conference, and I think my first point is already glaringly obvious. Roman data will be an ideal sandbox for machine learning. We are expecting rich, detailed, publicly available survey data that will be a great space to play. We have well-posed science questions, mostly cosmology in this room, but of course across astrophysics for Roman. And we have seen with previous telescope commissioning that the beautiful images really result in broad public interest and public support. What's less obvious, and I think something that we in the room need to wrestle with, is machine learning the right tool for Roman? Roman data are going to be, full of information. They are expensive to collect. And are the Roman data something that we want to trust with machine learning algorithms, right? Do we have the tools that will match Roman in depth and complexity, really the tools that Roman deserves? Do we have those? So the point I want to make today is that machine learning can be extremely powerful, but it doesn't see the way that humans see. Our ability to validate our training simulations is limited. Therefore, we should seek to understand our models and use best practices. And something you're probably wondering right now is why I've put the line breaks the places that I have, because this is a conference, not a poetry slam. And these are actually the 5 main points that I want to make. So we'll go through these 4 with examples for each. And then at the very end, I'm going to share 2 resources for best practices. There will be QR codes on the screen for those ones. All right. So machine learning can be extremely powerful. I'm going to focus today especially on machine vision, image recognition, and deep learning tools. And I want to take you back a little more than 10 years. So the figure I'm showing here are ImageNet competition results. So these are for classifying and appropriately labeling images. All right. On the x-axis is year. On the y-axis, error rate. So we want something that's closer to the bottom. And you can see something interesting. Error rate sat at about 30% until this friend in 2012. That's AlexNet. That was a deep convolutional neural network that changed the game, quite frankly, for image recognition. And then you can see from 2012 on, the winning teams really had jumped on this convolutional neural network bandwagon. And now convolutional neural networks really are sort of the beating heart of many machine vision and image recognition tools. For those of you who might not be as familiar with convolutional neural networks, they look something like this. You start out with an image that is then scanned with some convolutional filters to extract features from that image. Features might look like edges or corners or textures or gradients. Actually, in reality, they look much more complicated than that, and we don't have human words for them, but it's extracting the important pieces from that image. And then a fully connected network at the end looks at, how much of each of these features did it extract from the image. Therefore, what can I surmise actually belongs in that image? And so my point for this section is that machine learning can be extremely powerful. We've seen a number of examples so far, and I want to highlight a couple. The first one I want to highlight is from 2018. This is one of the earliest examples of deep learning in astronomy. Linus et al. Developed a tool called CMU Deep Lens. This was looking forward to Rubin data, developing a tool that could identify strongly lensed images in sort of sample postage stamps. They used deep neural networks, and the outcome of this is that their model was actually able to outperform humans, which we often take as being the gold standard. Machine learning it's not just outperforming humans that machine learning can do. It can speed up expensive computations. So Mila Shatter-Murray in 2023 looked at ways to paint baryons onto n-body simulations. So this is a way to take sort of our cheaper n-body sims and make them look like those more expensive hydrodynamical sims. Mila used a UNet for this, which is an image-to-image deep learning tool. And the outcome from this was that it not only reproduced the images, as you can see, the true and predicted images on the screen, but it also was able to reproduce expected scaling relations, which was a really exciting result. Julie McHenry pointed out to us yesterday that one of the exciting things that will happen with Roman is our ability to learn things from things we didn't expect, those new things that we're going to find. And machine learning can help us find those. Michelle Lochner developed a tool called Astronomaly Protege. This is based on, or it was originally developed for radio images, but it's pretty neat. It takes those images and it puts them into a lower dimensional space, and it looks around the edges, the sort of weird ones. And then it gives examples of those weird images to a human who can rate it from a 5, yes, I'd like to see more of these, kind of like Netflix, right? From a 5 to a 1, no, I'm not interested in those. So it is a way to find anomalies, but not just generic anomalies, the anomalies that are of particular interest to any given human user. And I think something like this is going to be really powerful for sifting through all of Roman's pixels. And machine learning can perform tasks that we don't have traditional methods for doing. John Soltis just this year published a paper that looked at galaxy cluster mass accretion rates. You are seeing on the x-axis true and on the y-axis predicted cluster mass accretion rate estimates. There really isn't a good sort of traditional tool for doing this, as you can see on the left-hand side. Though his method is noisy, it does manage to pull trends out of the images. Okay, so machine learning can be extremely powerful, but it doesn't see the way that humans see. What I'm about to show next is, I think, a paper that was extremely influential for my machine learning philosophy and the way that I approach my research. So if you've seen me give a talk before, you may not answer the following question. What is this? Anyone, you can just holler it out. It's a horse. Great. How do you know it's a horse? It looks like a horse. What else did I hear there?
It's eating grass.
It's eating grass. Yep. It is on a field. Others? It's a horse. It has a certain horsey quality, doesn't it? So the paper that influenced me and my machine learning philosophy so much looked at horse images and the way that they were classified, and found that the most important information in this image was a stamp on the bottom left-hand corner from the horse photographer that had contributed all of the horse photos to the training data. Okay, this is an image from that paper. Top left-hand side, we see a horse with the copyright stamp classified as being a horse. Take it away, no longer classified as a horse, all right? And you add the stamp to this picture of a red convertible, and with strong confidence, it's classified as a horse. See, and we just turned a bug into a feature. This is what I love about these crews. This is a tench, a type of fish that I did not know up until about a week ago existed. It is valued for being beautiful and ornamental. They are also used for food. The most important pixels in identifying this tench, I'm going to show you some examples. Also very common with anglers. And so the most important pixels become the fingers against the green background. Okay, why are we talking about horses and fish? If we're going to trust our pixels, our Roman pixels and our Roman data to deep learning, we want to understand what they're doing. What do you all see here? I heard an elephant and I heard a cat. We've got a neural network and some humans in the room. Guros 2022 found that networks that were trained on ImageNet were biased toward texture. They are more likely to see on the right-hand side when there's a texture shape cue conflict. They are more likely to confidently label according to texture rather than according to sort of that background shape. Here's another figure from that paper. The right-hand bar is humans' accuracy, and the left ones in blue and gray are neural networks. And you can see in the case of the silhouette and the edges, the human really outperforms, but underperforms in terms of texture. Okay, they're paying more attention to texture. We're paying more attention to shape, sort of in general. All right. Machine learning can be extremely powerful, but it doesn't see the way that humans see. And our ability to evaluate our training simulations is limited. So I've got an activity I want us to do here really quickly. I'm going to put up some data. You will see 13 different data sets. You're going to see their X and Y means, their X and Y standard deviations, and their correlations between X and Y. And I want you to tell me which one is the outlier. What do y'all see here? Someone say the obvious thing out loud. They are almost identical. So this is interesting. So why don't we take a look at these data points and just visualize them and see if the outlier becomes obvious. All right, these are the data source dozen. You can see the summary statistics up at the top. That's what you saw on the table before. So the mean and standard deviations in X and Y. Ooh, we're getting some, getting a little fussy there. Now that you've seen them all, does anyone have a favorite outlier? Probably a little bit subjective. I kind of like the dinosaur, yeah. All right, here they all are next to each other. We can tune our simulations to match simple summary statistics. But the fact of the matter is that even with those simple tests, we might not be able to capture important patterns or correlations in our physical models, right? We rely on simple summary statistics, which are powerful, but summary statistics are not a complete description of the kind of rich data that we're expecting from Roman. And so we have to proceed with a little bit of caution. The image that I'm showing on the right here is, on the left-hand panel of it is n-body simulation of galaxy clustering. That looks exactly like a room full of cosmologists would expect it to look. The right is, has the same power spectrum. And so, you know, the point here, I guess, is that the power spectrum, while extremely valuable, contains a lot of information, but not full information about the distribution of matter. And if our machine learning models are going to be paying attention to things beyond the power spectrum, we have to be careful there and we have to see them and understand. All right. Machine learning can be extremely powerful, but it doesn't see the way that humans see. Our ability to validate our training simulations is limited. Therefore, we should seek to understand our models. I'm going to show you 3 tools that you could use for understanding your models. This is not an exhaustive list. This is my 3 favorite. All right. So the first one we've seen already, this sort of pixel and feature level importance. My favorite tool for doing this is not the one that the Lapushkin paper used, but my favorite tool for doing this is something called saliency maps. Saliency maps move into pixel space and they calculate a derivative. They basically ask, if I change this pixel value, how much does the output change, right? How sensitive is the output to this particular pixel? And then you can build a heat map from that. And while it's extremely challenging to take that heat map for a natural image and make any sense of it, for astronomy, it's actually quite easy. We've got some, rotational invariance. We sort of understand what's going on in the image. We can zoom in on certain parts of a galaxy, and so we can use something like saliency maps to make some sense of what is this deep learning image tool seeing, where is it paying its attention, and why. Right? We can start to understand some science beyond that. The second is adversarial attacks. So this is the second of the 3 I want to present to you. So up on the screen, I've got a picture of a panda and a gibbon. I'll give you a hint. A gibbon is a type of monkey. Can you tell them apart? Great. Up on the screen, I've got something that machine learning would classify as a panda and a gibbon. Can you tell them apart? All right. This came from an interesting paper that looked at adversarial attacks. What an adversarial attack does is it says, okay, I see you've got your image and you've classified that as a bird. What if I wanted to scoot this classification and change it? What if I wanted to classify it as a dog? How would I change the pixels to be able to do that? Goodfellow 2014 had this panda image. Through an adversarial attack, added the noise that you see in the middle. Now there's an epsilon multiplied by that noise, right? So it's really been ramped up so you all can actually see it here. to, with 99.3% confidence, classify the image on the right as a given. What's going on there? You know, in high dimensional space, I'm going to gesture in 3D, but imagine it in like, I don't know, 1,000 dimensions. In high dimensional space, you've got some space that is classified as a panda and another space that's classified as a gibbon. And what they did is they, you know, perturbed that image in the direction of the gibbon into probably some space that had not been probed before so that it would be classified. Some would argue that this is a bug, right? It is not classifying the way that humans want it to be classified. Others would argue that this is a feature. It is more sensitive than my human eyes and can, you know, pull information out of that image that I can't. And is it a bug? Is it a feature? I think it depends on the use case and how careful you are with work that you're doing. Another example of an adversarial attack, Kiefer Sutherland and Reese Witherspoon, probably have never been shown in an astronomy talk before, but there's a first time for everything. I think most of you could confidently tell the two of them apart. The glasses on Reese Witherspoon in the middle panel make facial recognition classify her as Kiefer Sutherland with high confidence. All right, you can think of it this way: those glasses are the most Kiefer Sutherland thing to be. They are more Kiefer Sutherland than Kiefer Sutherland himself, and they fool the facial recognition into believing. This is just another adversarial attack, just rather than the noise being in the background. Now the noise is confined to some glasses. The final way that I want to highlight is you can understand with stress tests and out of domain. All right. Here we've got a school bus on a snowy scene. This one's actually an artificial image, a few artificial rotations, and then the one on the right-hand side actually is an unfortunately toppled over school bus. That is a real photo. Of course, in the left-hand side, correctly classified, and the other one's incorrectly classified. You can stress test your models by giving it, you know, surprising data or things that it's maybe never seen before, and try to understand the results. See what the failure modes are and understand the limitations of the tool. All right. Machine learning can be extremely powerful, but it doesn't see the way that humans see. Our ability to validate our training simulations is limited. Therefore, we should seek to understand our models and use best practices. So I've got 2 QR codes that I want to share with everybody. They also will be on my conclusion slide if you missed them. The first thing that I want to highlight is Hello Universe. This is a pairing of pedagogical code with curated data to teach machine learning to novices. So what we're seeing, folks, this is hosted at Mass, and what we're seeing folks doing with this is not only using it for self-teaching, but also in classes. We're seeing folks taking these data or these notebooks, swapping out the data sets for their own, or perhaps swapping out the method for something new, and using that to kickstart new research. I did say that the notebooks that are there now are aimed for novices, but if you are more of a machine learning expert and you would like to contribute one, please do contact us about that. The second resource is a paper called Constructing Impactful Machine Learning Research for Astronomy, Best Practices for Researchers and Reviewers. And in this paper, we go through 6 ways to make your machine learning research really just impactful and make it the best that it can be. So is machine learning the right tool for Roman? I would argue yes, but we need to proceed with caution. We need to be careful. We need to think carefully about the tool, make sure that we understand it and stress test it, and really try to build the tools that the astronomy community will trust. Thank you very much.
Questions? Yeah.
So I don't think it was your intention to make us extremely skeptical against machine learning. So, but everything in your presentation was mostly focused on how we should research machine learning, in terms of machine learning. But for us who don't research machine learning, who want to adopt the research machine learning models, how should we read the published papers critically?
Love this question. So my intention actually was not to make everyone skeptical. My intention was to give you new tools for approaching your own research with care to make sure that it's robust. And I actually decided, it was an intentional choice. I decided that I think through the rest of the conference, we've already seen in the past 2.5 days, there are a ton of great applications of machine learning, and I didn't need to tell those again. So as far as how do you approach and how do you evaluate, I'll actually say that at the end of this paper in the appendix, we've got sort of a rubric for evaluating a paper. So the rubric in that is intended to be kind of for reviewers to be able to look through and be able to sort of understand. So the things we're asking here are, are you comparing against a reference? Is your goal to make it better? Is your goal to make it faster? Tell me how it compares to the state of the art. Are you using best practices? Are you being really careful with your vocabulary? Are you trying to interpret and diagnose your model like I showed you here? We go through, a number of different things, but take a look at the appendix because that is really intended to be like a quick start guide.
Thank you.
Other questions?
So they're saying that, can you talk about the availability of labeled, in parentheses, ground truth not simulated data that would be specifically applicable to supervised machine learning training for Roman and Euclid large-scale imaging service?
Yeah, absolutely. So the question here is about labeled versus unlabeled data. For something like simulation-based inference, you would want to train on a simulation that has labeled data and then test on reality. And as far as the availability of labeled data, it depends on the science question. It depends on what you want to do. The places that I would start are actually the simulations that were highlighted in this morning's session that are being put together both by the PITS and on site here at Space Telescope. Those would probably be the places that I would start, depending on the science case.
All right, any last questions? Okay, well, let's thank Michelle again. So our next talk is by Ashod Kaderlarlian, and he's going to tell us about photometric redshifts for Roman using.
Yep, thank you. Hi everyone, my name is Ashod Kaderlarlian. I'm a PhD student at the University of Pittsburgh, working with Jeff Newman and Brett Andrews. So I'll talk about deep learning photometric redshifts for the Roman Space Telescope. Just jump right into it. So I want to emphasize this work is primarily focused on improving the performance of individual photometric redshifts for galaxies, and we want to make use of we want to make full use of the Roman data to obtain the best possible photo-Zs, and this could lead to improvements in clustering measurements, studies of galaxy evolution and formation, and even large-scale structure measurements. And so, traditionally, the way photometric redshifts have worked is you have imaging of a galaxy in multiple bands. In this case, I'm showing 4 HST bands. And you would integrate the flux of each galaxy within a band and plot this flux as a function of wavelength. And that would give you a coarse-grained version of an SED. And you can use this to predict the redshift. So it's kind of, you can think of it as a compression, where you're compressing each image into just one feature, which is the integrated flux, right? And more recent methods have actually moved on to using convolutional neural networks on the images directly. And so you would input the 4-band imaging and output the scalar redshift. And given a training set of images and redshifts, you can minimize the loss function and get better results this way by leveraging pixel level information from the images. And so these studies, though, have been limited to low redshift bright nearby galaxies just because of the availability of training sets. So for example, SDSS data. Roman will make it possible to use these deep learning algorithms on high redshift galaxies for two main reasons. One is availability of data. So if we want to use deep learning algorithms, we really need to resolve the morphological shapes of galaxies. And at high redshifts, we can only do that with space-based imaging. So Roman is great for that. And also for having more spectroscopic labels too. So we'll have spectroscopic labels from Roman zone spectroscopic or GRISM redshifts, or from ground-based spectroscopic instruments. But that's not necessarily true for fainter galaxies. But in general, we'll have enough data to start training these deep learning algorithms with Roman. But the images that Roman will take, or the populations of galaxies that Roman will observe, will be significantly different than, say, SDSS galaxies, right? So the first question is, will deep learning even work for these galaxies? Will we get better redshift measurements than photometry? And which algorithm do we use? Right? There's been many algorithms developed based on these ground-based image nearby bright galaxies. So it's not unclear which algorithm would give us the best results. And so these two main questions are the questions that we're tackling with this work. And so to answer these questions, we're going to use Hubble data. So that's for two main reasons. I'll just quickly go over it. It's because of similar wavelength coverage. So these I'm showing 4 HST transmission curves here. And it's we have some similar wavelength coverage to, in particular, Roman's wide area medium tier imaging. And also spatial resolution. Like I said, we need good spatial resolution to resolve these morphologies and use deep learning. And so Roman will have similar spatial resolution to Hubble, right? And so in particular, we use the Hubble candles imaging data set, imaging survey. Here I'm just showing a few examples of the images in the 4 bands. And candles has detected roughly 250,000 images. And so after making some selection cuts, we end up with 100,000 images to work with, and 20,000 of them have redshift labels we can use to train algorithms with. I do want to emphasize, Roman will image hundreds of millions of images, of galaxies. So this is by no means data set comparable to Roman, but it's enough that we can test algorithms. And so when I talk about results, I want to talk about different deep learning strategies. One is fully supervised, which is what most people are familiar with. It's essentially you use the labeled data to train a neural network that learns the relationship between images and redshift, and then you can use that network to predict redshift for the remaining galaxies. But we have more galaxies, 80,000 in our data set, that don't have redshift labels. So can we make use of them to get even better redshift estimates? And so we're going to test self-supervised algorithms and also semi-supervised algorithms, which make use of the unlabeled data. Now, to show results, I will essentially show 3 metrics that are based on the normalized residual on the top right, which is essentially just the prediction error. And the first metric we define is the bias, which is the mean prediction error. And the second metric is the normalized median absolute deviation, which is essentially the spread of the prediction error. So it's a robust, statistically robust version of the standard deviation. And the third metric is the fraction of outliers, or the fraction of objects that have delta z greater than 0.15. And if I'm sure you've noticed here I have an x-axis, which is the fraction of labeled data. So I'm going to show these metrics. So yeah, we had 20,000 labeled objects. After doing a training, testing, validation split, we end up with 14,000 objects in our training set. And so I want to show these metrics as a function of fraction of labeled data that we use for training. And that's for 2 main reasons. The first reason is it's a good argument for spectroscopic measurements, because as we'll see, as we add more data, we'll get better results. And the second more important reason is that these extreme regimes of low number of fraction of labeled data and high number of labeled data correspond to essentially faint and bright galaxies. So we're not going to have that much labeled spectroscopic redshifts for faint galaxies. So we care about the performance of these methods for these different regimes. And so that's why we show it as a function of this x-axis. And the plot you've been looking at shows the performance of the photometry, traditional photometry-based predictions. Okay, we see in general just improvement as a function of labeled data, and these white curves will act as a benchmark to which we will compare the more deep learning algorithms. And so the first result is using only the labeled data, so training a supervised convolutional neural network. And we see it performs better than photometry, especially when we use all the labeled data. But importantly, it doesn't actually do better than photometry when we don't have a lot of labeled data. And that's kind of expected because to train a deep neural network, you need lots of data. And photometry offers a more efficient way of encoding the information if you don't have a lot of labeled data. Okay, so yeah, we have 20,000 labeled data, 80,000 unlabeled. So with fully supervised algorithms, you're throwing the unlabeled data away. So we try to make use of it with a self-supervised task. So now to train an algorithm with unlabeled data, you either need to come up with pseudo labels or a surrogate task for which you can write a loss function and minimize it. So in this case, the surrogate task is contrastive learning. And the way it essentially works is that you generate two views of an image. And you write down a loss function that if these two views come from the same galaxy, you track them in this low dimensional space that you're learning called latent space. And you push away the galaxies that are different galaxies, of different images of different galaxies. So this way, you learn a low dimensional representation or a latent space of galaxies that's robust to the transformations you use to generate the views. In this case, we're using rotations. And I just want to quickly highlight, this has been applied on STSS data, and it has worked. And we tried it on our data set, and it didn't work. Essentially, we think it's because of the dynamic range of our data set. So again, it comes back to Roman having different data and much deeper data that has a wide range of magnitudes and morphologies. And so we have to be careful about applying these algorithms that have been optimized for, say, low redshift galaxies to high redshifts. To kind of assess this, we looked at the low dimensional space, latent space, by using UMAP, which is a dimensionality reduction algorithm. So we project this space onto 2 dimensions and make scatter plots. And we essentially see a problem here. If we don't see a very smooth gradient with redshift, which means that this space is not good for redshift prediction. And if we make color plots of magnitude and color, we see that it captures magnitude fairly well, but it's not capturing color, which is to first order what determines redshift. And so we want to use to have an algorithm that learns a latent space or a low dimensional representation of galaxies that encodes color information. And so I don't want to go into the details here, but we essentially add the contrastive learning loss function. We add to it a color prediction loss and a redshift prediction loss. So we combine loss functions and we sort of align the latent space in such a way that it captures color information and redshift information in a much better way. And you can visualize this here where you see much more clear gradients with redshift and magnitude and color. And these are the results for the semi-supervised algorithm. So we do better in all cases. And importantly, we do better than photometry, even if we don't have a lot of labeled data. And that's crucial for Roman when we apply these methods for faint galaxies for which we won't have that much labeled data. And we do better for bright, if we have more labeled data too. So for both faint and bright galaxies, this will yield better results than photometry alone. And if we limit the calculation of these metrics to the brightest galaxies, which have better signal-to-noise imaging and more robust labels, we see some interesting patterns. So first of all, photometry starts plateauing. So as we add more data, we don't expect to see performance improvements. But for the deep learning algorithms, and in particularly the blue semi-supervised algorithm, we see that it's it will keep on improving and scales better than photometry or even supervised. So I will conclude with this slide, which shows this latent space with the galaxy images. So you can clearly see the different galaxies that have different properties and are well separated in this latent space. So to answer the first question, will deep learning work? We use Hubble data to answer that question. And the answer is yes. And so, but we have to be careful about the algorithm we're using. We want to use an algorithm that makes use of the labeled data and the unlabeled data and leverage domain knowledge and make sure, important features like color are encoded in these representations. And finally, I just talked about redshift, but these low dimensional representations can also be very useful for finding anomalies, predicting other properties or classification, and just parsing through all the petabytes of that data that we'll be collecting. Thank you.
Thank you. Any questions? Yeah.
Thank you for the talk. So how do you make sure that the training data that you're using to train this deep learning is representative of the full data you want to get the results from? So, for example, you said that for Rubin you cannot have the objects for this data for faint galaxies. So, how do you know that the training data will also work for this faint galaxies?
So our data set contains, contains faint galaxies up to, plot I was looking for. So the plot on the right shows, the H-band magnitude of our data set. So it goes up to 26 for the unlabeled data, and there's some labeled data there from the spectroscopic labels. So essentially, the metrics we calculate are on a test set, which the algorithm doesn't see, and it is across this magnitude coverage, which we expect, that's roughly where the 5 sigma Roman depth is for the wide field. So.
Yeah, back.
This is really interesting. So in your UMAP montage at the end, I was struck by the fact that it seems to be sorting on the noise in the images.
Yep.
Can you talk a little bit more about that? Because you do expect that more distant galaxies would be smaller and noisier, but is that primarily what it's picking up on, or is that more an effect from the cause of this arrangement?
No, it's definitely one of the features that the latent space is encoding, which is just magnitude. And we want it to encode magnitude. We want the faint objects to be separated from the bright objects. And yeah, you just see the noisy images because they're faint galaxies, and that is something we want. So.
Yeah.
Yeah, do you see significant degradation in really crowded fields where you might have blending, or just other objects inside the little posters?
Yeah. Yes, so we think that adding a color loss helped with that. So with the initial contrastive learning, that was a real problem because you have other galaxies in the field and you're doing rotations, and then the algorithm is putting them near each other, being near neighbors, and then that becomes a real issue. But when we added these other loss functions, it kind of really is forcing the algorithm to focus on the main target galaxy. Yeah.
All right, one last question in the front.
So 3 of those metrics to train the model.
Mm-hmm.
How do you balance the ratio or importance of those? Because if you have too much importance on one of them, they might kind of overfit those while ignoring the others. So how do you balance those?
Do you mean the 3 loss functions? Right?
Yeah.
So I just normalized them to have the same order of magnitude. So we played around with different weighting. I'm still experimenting with that, but so far it seems like it doesn't really make much of a difference as long as they're roughly same order of magnitude.
Okay, well, if you have other questions, up with Ashad later, coffee break or after this. So let's thank him one more time. All right, so our last speaker of this session is Yunhao Zhang, and he's going to tell us about precision cosmology with data augmentation.
Yeah, hello everyone. I'm Yunhao Zhang. I'm a final year PhD journey at the University of Edinburgh and Leiden University, working with a long list of wonderful people. And I'd like to talk about the research throughout my PhD, which is with the title of Advancing Stage 4 Precision Cosmology with Data Augmentation, Efficient Marginalization, and Accelerated Computation. And I think we have, oh, sorry. Oh, yeah. I think we have already seen this plot many times, and from the DESI result, we see the dark energy might not be a cosmological constant. But from my perspective, it's still under debate. It's a new physics or new systematics. And that's why we think we need Rubin, and Euclid, which can provide independent constraint on the property of the dark energy to validate if we can find the signal of new physics in a self-consistent way. And the way I do cosmology focus more on the wavelength and large-scale structure. And basically, like, we decompose the galaxy sample we have into the background source galaxy with good shape measurement and the foreground lens galaxy with good like redshift estimation. Then we can do like autocorrelation on the shape for the source and the cross correlation of the position of the lens with the shape of the source. That's the galaxy-galaxy lensing, or the autocorrelation of the lens. That's the galaxy clustering. That's known as the 3x2-point analysis in other talk. But we know these are all photometric surveys, so we strongly rely on the technique of the photometric redshift. The traditional way is to use a library of SCD templates, but it will require you have a precise knowledge of what's the prior of the templates. And nowadays, people start looking at the machine learning, but for machine learning, the major challenge is the training data you have spectroscopic redshift usually targets bright and low redshift galaxy, which is not representative compared to the photometric galaxy you want to like apply your machine learning method. And I want to emphasize the lesson we learned from the Kids Legacy cosmological results is the technique we calibrate redshift and also the sample with spectroscopic redshift is the two major drivers that change the constraint on the S8 from a 2 sigma tension to almost consistent with the Planck CMB. So that's very important, and we need to be careful. And in the first topic, I would like to show how we improve the photometric redshift, the point estimation, and the calibration. And the way to do that is to use the self-organizing map-based data augmentation. So the self-organizing map sum is a machine learning dimensionality reduction algorithm. So it's basically project your high-dimensional galaxy SCD into a 2D map. And here we use the sum to train on a LSS year 1 photometric application data derived from Open Universe Small Galaxy Catalog. And then we apply the pre-trained sum to a spectroscopic degradation data set where we mimic the spectroscopic sample we expect to have for the LSS year 1 cosmology. And we can clearly identify the region that we have missing spectroscopic information. And then to compensate the missing information, we take simulated galaxy from another catalog, which is a Cosmo DC2, to occupy the missing SCD we have. And if you combine the spectroscopic degradation data sets in the top right with the simulated augmentation data sets in the bottom left, you will have a much more representative combination data. And in the sum space, you can see the distribution between the training and your photometric application is quite comparable. And we also show that the sum-based data augmentation is very effective to augment the faint and high redshift galaxy. And the redshift distribution of our combination data sets show as the blue line is very similar to what we have for the application photometric data, which is shown in the black line. So if we can train on this more representative data, we found the photometric redshift can be improved. If you don't do data augmentation, the machine learning follow Z you got for the higher redshift galaxy is almost totally wrong. But with the data augmentation, we find for the average of the biases and also like the scatter of the biases, outlier fraction, and also the information loss of your galaxy individual PDF or get reduced. And here I'm showing only using the Rubin optical colors. I believe with Roman in the near infrared, these things can be further improved. And here I'm talking about how data augmentation improve the point estimate of each individual galaxy. And the next thing is how data augmentation can improve the calibration of the redshift distribution for an example of galaxy. And the way, the way in cosmology, we trace the cosmic structure growth is we divided the lens or the source sample into multiple tomographic bins, and based on the photometric ratio of point estimate. And the information is we want to know is the redshift distribution of each tomographic bin. And that's the things we want to calibrate. And here I'm showing how we do the calibration. And the black line is the histogram of the true redshift, which is like the ground truth as reference. And the blue lines refers to the conventional calibration technique, which is using a sum, like to associate the histogram of your spectroscopic redshift to the corresponding photometric counterpart. And the green line is something new, which is the stacking of the PDF. Usually you cannot really do that because the PDF training on a non-representative sample is very bad. But here, benefiting from the data augmentation, we have a more representative training sample, and we have much more improved PDF. So stacking the PDF already give you overall reasonable shape of the redshift distribution. And the green line is showing if you combine two different independent estimator of the redshift distribution, it can further reduce the biases you have in your redshift calibration. And here I'm showing a forecast for LSS year 1 redshift distribution for both lens and source sample with realistic uncertainty. And there are two components. One is the statistical uncertainty. You can see this sharp wiggles on that, which mainly come from the bootstrap error. And we also have the systematic uncertainty, mainly due to the spectroscopic selection function that will dramatically change the shapes of the distribution. And here I'm showing how we evaluate the precision we have for the redshift calibration using the mean redshift of the distribution. And here the gray band in the right is showing the science requirements for the Rubin derived purely based on the statistical uncertainty. And for the lens sample and the low redshift source sample, the biases we got is minimal, and we can very well satisfy the science requirements. And also we see that the width of the histogram is always broader than the gray band, which means the systematic uncertainty we include in our analysis is dominated over the statistical uncertainty. That's the thing we need to be careful for our future cosmological analysis. That leads to the second topic is how we can better parameterize and marginalize over the redshift distribution uncertainty. The conventional way we do that is we assume a fixed shape of your redshift distribution, and we only allow single 1 degree of freedom to shift it along the redshift axis. Then you will ignore all kinds of variation in the shape. So to improve that, we introduced the machine learning algorithm variation autoencoder, which is like a nonlinear way to do the PCA. So we take the redshift distribution as the input. We use a neural network as the encoder to compress it into a low-dimensional latent space. And after resampling in the latent space, we use another neural network as the decoder to going back to the redshift distribution. So the training is to minimize the loss between your inputs and outputs. And here I'm showing for all the redshift distribution we have with all kinds of realistic uncertainty. If we first do a PCA, we found we need almost 100 primary components to recover over 99% of the total variance. To further reduce the dimensionality, we apply the convolutional neural network on the PCA coefficients. And in the end, we find we can only use 5 latent variable for the lens and 5 latent variable for the source to describe all the uncertainty we have. And here I'm also showing if we fix the 4 latent variable to be 0 and only resampling single 1 latent variable and go through the decoder, we can precisely reconstruct all kinds of noisy features we see in the redshift distribution. And the color bar in the right is showing the value of your latent variable. So this can be a better way to define the nuisance parameter where we have a standard normal distribution prior and can better marginalize over the redshift distribution uncertainty. However, we still need to sampling those nuisance parameters in our MCMC, which is not ideal. The next step is if we can find an analytical relation between your data vector and nuisance parameter, we can directly marginalize over them like to estimate the posterior analytically. So, but it's difficult because here I'm showing the shear angular power spectral, which is an integral along your line of sight over the Lenzing kernel function and the mass power spectrum. And the Lenzing kernel function is also an integral over the redshift distribution. So it's like a triple integral. So this triple integral is the reason why it's difficult to find the explicit relation between the data vector and your redshift distribution. And to do that, we divided the like a large range Limburg integral into many small integrals based on the grid we have for our redshift distribution. And within each small integral, we can approximate all the physical quantity by a piecewise linear function, like for mass power spectral, redshift distribution, scale factor. And after we're doing that, we can solve each small integral purely analytically. And the advantage of this mathematical formalism is in the end, we can find the analytical expression of the angular power spectrum, which can be written as a double sum over a cosmology dependent coefficient tensor times the quadratic order of your redshift distribution. And if we calculate CL in this way, we find it can achieve percent level accuracy compared to the standard cosmology library if you do numerical integral. And on CPU, we find we have comparable computing speed. And now we are developing JAX-based GPU parallelization because we translate the triple integral into a purely tensor operation, which can be very fast to run on GPU. And also because we know there is a quadratic relation between CL and redshift distribution, it can allow for fully analytical marginalization in future Hubble analysis. And due to the time limit, I will stop here. And the first two papers describing about sum-based data augmentation for point estimate and redshift calibration are now under the DESI internal review. And we are now running the forecast for LSSD cosmological constraint using our VAE marginalization and compare how that would improve the error budget estimation. And the last two work is now in preparation. And I'll stop here and feel free to ask any questions.
Yeah, Justin.
Can you say more about how the selection function of existing spectroscopic data is accounted for or modeled in your when determining where to sort of augment?
That's something. I will just say it. I think the way I do it is, oh sorry. Yeah, here. Yeah, the way I do it is like when I do calibration, I have like 500 different realizations with different photometric noise, with different spectroscopic selection function. And in the end, I assume the marginal redshift distribution is a linear combination of each conditional redshift distribution. And then you can first, for each conditional redshift distribution, you can implement the statistical error using Bootstrap. And for the systematic error, I assume the linear coefficients follow some probabilistic distribution function. Then I can also probabilistically propagate different selection function into the resulting redshift distribution. And in that case, we can take both error into account.
All right, Jamie.
I have a question about the simulations that you're using to augment the data we saw.
Yeah.
Are you concerned in systematic biases in perhaps simulation colors of those galaxies do not look like the actual universe that you'll
Yeah, exactly. That's actually the major driver of the systematics we have here. But I would say, like here, let me try. Yeah, here this plot is showing the color redshift distribution for the two different simulations. And you can see the Cosmos DC2 is quite different from Open Universe. But we don't use Cosmos DC2 as its original form. We first weighted resampling the Cosmos DC2 in a sum space to match that to the Open Universe. And here you see the color is quite different. But after the weighted resampling, we found the UMass G over GMass R color augmentation data is quite similar to what we have for the application data. So in real case, you need to resampling your simulation to match the observation. That's a takeaway message.
Did I see? Yeah, go ahead.
Could you go back to the corner plot of the nuisance parameters?
Yeah.
Yeah, I have two questions. Like one is like, how did you choose like 5 parameters? Like, did you try 4 and 6 and the 4 was not enough or something? And also, second question is, the nuisance parameters corner plots are very circular, and is it like typical in VAE, or is it just your special case being somehow symmetric between those?
Yeah, it's a very good question. I don't have time to describe before. Like here, I choose 5 because it's a little arbitrary to choose which one. I can choose 4 or 6.
Yeah.
I choose 5 maybe because if I only use single one shift parameter, I will have 5 parameter. Now I want to say with the same number parameter, I can describe more uncertainty. But in practice, you can do 4, 3, or even 2. But that will require your VAE model architecture become more complex to really do that. And the second question is about like why the corner plot is so circle. That's one of the feature of the variation autoencoder. We have a loss function that to make sure the latent space follow a standard normal distribution. So very simple means that loss is very small, and also means that those latent variables follow standard normal distribution. So they're easy to sample and they're easy to have a good prior, and we can easily marginalize over them.
All right, let's thank Yun Hao again. And that brings us to the close of today's talks. Just a few announcements. So right after this, there's the SDS happy hour, which is just in the cafe over there. Free beer, so you should go there. And then I know there's a early career gathering at Nepenthe Brewery, and that, yeah, maybe you can go whenever you're done here. There's also the Deep Space Dialogues tonight at 7, so that's going to be virtual only. So originally we were thinking about showing it here, but then just thought it might be a little bit too much effort for all of the different parallel events going on. But you can catch that streaming, so please do connect if you're interested. And yeah, we'll see you again tomorrow morning. So thanks.